This media was gratuitously produced by Clear Contributions Audio and Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
Orbital size. What's the effect of the orbital size? Do you want a smaller orbital or a larger? I guess what I'm saying is, do you want to have more p orbital character or less p orbital character if there's a carbanion? Less. Because if you have less p orbital character, then it's going to be a little bit smaller orbital, and you want to have the negative charge a little closer to the positively charged nucleus. That's a little bit stabilizing for it. And then resonance. What's the deal with resonance?
It's cause it to be more stable.
More resonance, more stable. Yay, go resonance. And that's going to be the biggest stabilizing factor that you have. So putting those together in an order, resonance is the most important factor. So if you have resonance stabilization, that's going to be the best. Then the next most significant feature is the size of the orbital. That's a whole lot more important than what's going on next door with bond overlap. And so if you have a triple bond, then that's going to tend to be a little bit better carbanion than a double bond. Which is better than the single bonds. As far as the single bonds go, then the hyperconjugation plays a role. So methyl's better than primary, better than secondary, better than tertiary. Just like before, if you understand the if you understand the relative stabilities, then you can analyze reactions as you're going along and just find the most stable situation you can.
How is methyl different from primary?
I'm glad you asked that. Methyl is where you have just the carbon by itself. A primary would be where it has one carbon attached to it. Any other questions about that? If you have one take-home message, that's probably one of the biggest ones right there.
It doesn't make a dumb question, but a double bonded carbon is still a primary carbon, right?
It might be. Yeah, it could be secondary.
Yeah, just because it doesn't have two bonds doesn't make it a two prime, right?
Right.
Okay, just making sure.
It's just the number of carbons attached,
Right.
not the number of bonds.
Gotcha.
That's good for clarification. Okay, and then we just have, I think one more page and then we'll be caught up. No? Oh well, a little over a page, we'll be caught up. So there were 4 situations that I told you where if you see it, then you're going, oh, I better watch for a carbanion. One of them was if you have something that is not a fantastic leaving group next door. Because if you have that, then you might want to use the electrons right here in this bond. They might go towards the carbon next door because it's electron deficient, because you have the leaving group is something, electron withdrawing is the idea. And the electron withdrawing thing can come off. We're going to be talking about this in like 3 or 4 more chapters, so we're going to hit it really hard. So if you don't kind of get the idea right now, just kind of tuck this in the back of your mind. We're going to get to it later. But the idea is if that leaving group, the Y, doesn't come off really well, then the hydrogen might be removed, and then you got a carbanion temporarily until you can share the electron pair. So what I highlighted in yellow, that could become the electron pair for the carbanion. Okay, but the stuff for this chapter that's going to be a whole lot more immediate for you, if you have a carbon that has MgBr on it or any other metal, then because magnesium is so much less electronegative, and because you have a metal-non-metal combination, that is really the same thing as an ionic compound. It really behaves like that, where you almost have the magnesium and the carbanion hanging out together just because of the opposites and charges. Okay, so if you see the MgBr, that's going to be the most common one with a metal that you're going to see in this class. If you see that, then just you can erase the MgBr and put a carbanion on there. Okay, another case where you might see a carbanion is if you have a terminal alkyne, it's called. A terminal alkyne is one where you just have one of the carbons with a triple bond is on the very end. And so therefore it has a hydrogen. If it was buried in the middle, it would have carbons on either side, so you couldn't do this little trick. But if you see that, plus a really super strong base, this is going to be the most common one you see, that base can rip the hydrogen off. That's because that carbon is sp hybridized, and so it's up here in the right after resonance deal. It's not super acidic, so you have to have a super strong base, but if you have that combination, then that's what you're thinking. Okay, and if you want to be a purist, I'll put the NH3 in here too, but we're mostly focusing on the carbanion. And the third situation that I'm hoping to get to today, actually, is if you can set up resonance as a result of creating a carbanion. And the most common thing we're going to be talking about is if you have a carbon that has hydrogens, and it's right next door to a carbon with a double bond to oxygen. The carbon double bond oxygen is called a carbonyl group. We're going to be doing 2 whole chapters on carbonyl groups, so you're going to see them. But just for right now, it's a whole lot easier if you can picture what I'm saying without me saying the carbon next door to it that has a carbon with a double bond to oxygen. Carbonyl is so much faster. You notice that if that is right next door, then if you rip that hydrogen off to create a carbanion, oh, look, you have resonance. And that's why it is a somewhat acidic hydrogen, because if you pull it off and you create resonance, then that's going to be something that's pretty good. So we talked about the Grignard, which is the one with magnesium bromide, on Friday, and we also talked about pulling off the hydrogen from that carbon with a triple bond. I'm hoping to get to the last case today. Okay, definition of a Grignard. Yeah, it's specifically Mg with some halogen. Usually you're going to see MgBr. If it has other metals, that also can be used to make that carbon a nucleophile, but it's not called a Grignard specifically. So yeah, anyway, Grignard is what you are most likely to run into for a standardized test, for instance. And I really want to get to the carbonyls, so let's see. We'll just fill in what we had done before. Why a Grignard reagent acts as an ionic compound? Metal, non-metal, yeah. You got such a huge difference in electronegativity that it's ionic. And then why a strong base can remove or can create a carbon ion in a terminal alkyne? Yeah. Yeah, and this is it's only sp hybridized, so it has a smaller orbital. Yep, it's second on your list of stabilities. And the base that's commonly used is NH2 with a minus charge. And I wish I would have had enough room left on that line just to put it at the end of the line. It just didn't deserve an entire line there, but I couldn't fit it. Okay, I think we can get there. Okay. Then, direction of electron flow if you're doing a carbon ion with resonance. What you think? Goes away from the negative charge. Because remember, electrons are what you're moving. Electrons have a negative charge, so they always go away from a negative charge or they go towards a positive charge. But since we're talking about carbon ion here, it's going to go away from the carbon ion, away from the negative charge. So when you're drawing the resonance contributor, how do you make room for moving the electrons from the carbon ion over? Uh-huh. That's right. You gotta, the one that I have highlighted in yellow here, you gotta unplug those electrons from that carbon to make room for the new electrons coming in.
Wait, I didn't really know that. What did you just say?
Oh. So you're moving these electrons away from the negative charge because the problem is you have too much negative charge. If you were going to just make a double bond here, though, then this carbon would have too many bonds because you'd have 1, 2, 3, 4, and then the hydrogen would be 5. So the only way that you can make room for this coming in is to move these electrons over to make way for these electrons coming in.
Oh, okay, that makes sense.
Yeah. Okay, and since resonance was an issue on the final, what patterns do you see here that will help keep you on track for drawing the resonance contributors correctly the next time?
Single bond, double bond.
Yep, you do box in the area. That will be helpful to make sure you're not going outside and resonating things that aren't allowed. Box in the area and work in groups of 3. Even if the resonance area is bigger than that, you always just look at 3 atoms at a time. Within that group of 3, the double becomes a single bond. The single bond becomes a double bond. And whatever it is you're resonating is going to appear on every other carbon. And that kind of bypasses all the theory about the electron wave patterns and constructive and destructive interference. But the important thing, I think, is for you to be able to figure out what are all the contributions to the actual molecule. So, all right, and then the last thing that I want to, I don't have that as an example there. Oh, well. Last thing for resonance is if you have multiple sources for electron pairs, you're going to pick the carbanion, first off, because that's the negative charge. So that's the one that has the issue. And then you resonate towards an atom that has a pi bond you can let go of. So you don't want to resonate this electron pair because when you move it down to this carbon here, there's no pi bond for it to let go of to make way for it. Otherwise, the only thing you can do is break the molecule apart or have carbon with too many bonds and everything. So the two concepts needed to choose correct non-bonded electron pair. You want to resonate the carbanion because that's where the issue is, and move the electrons towards an atom that you can let go of a pi bond. So you're not breaking the molecule apart, you're only moving electrons.
Wait, so resonate the carbanion and move it positively charged, what you said?
And move it towards a carbon that has a pi bond you can let go of, or an atom that has a pi bond you can let go of. So if you moved them from the oxygen down to the carbon, there's no pi bond for that carbon to let go of. And then the last thing we did was make sure you're focusing on groups of 3 atoms at a time when you're doing resonance contributors so you pick up all the contributors. Okay, then you practice, practice, practice. These are the same practice problems as you have in your handout, or in your textbook chapter, so you can always rework those problems and make sure that you can do them. But now, I wanted to get to this today. Unless, before I go on actually, any questions about anything? Okay, then today I wanted to do acidic alpha hydrogens and ketoenol tautomers.
What was that last one?
Ketoenol tautomers. Mm-hmm. You got to throw that one into your dinner time conversation sometime.
I'd like to swear at them.
Okay, if you have a carbonyl compound like this, you're going to see in the next chapter when you start naming them that when you do common name nomenclature, that you identify the carbons as you're going away from that carbonyl carbon using Greek letters, alpha, beta, gamma, delta, and so on. So the alpha carbon is any carbon that is exactly next door to a carbonyl carbon. It doesn't have to be to the left, and you don't have to have just one. You might have 2. So what I'm saying is the definition of an alpha hydrogen then would be a hydrogen attached to an alpha carbon, and an alpha carbon is anyone that's directly attached to a carbonyl carbon. Bless you. So I do better with pictures usually. So if you were going to diagram a picture of this.
Real quick, how do you identify the central carbon? How do we know which one to go off of?
Let me see. I'm not sure if I understand the question, but let me go back. So,
Oh, gotcha.
Yeah.
Well, yeah. But so is it just the one that has a double bond?
to oxygen.
Oh, to oxygen specifically. Oh, okay.
Yeah, so any carbon directly attached to that, so that it's going to be an alpha carbon and it could have hydrogens attached to it. You might have more than one, and either one of them could be acidic. Okay, so the reason why, once again, and I had already kind of gone over this, but the reason why that might be an acidic hydrogen, in other words, and the reason why that might be able to come off is because then you can go from not having resonance to having resonance there. It'd be better not to have the negative charge there at all, but because of resonance, it's a doable reaction. Okay, so if you see a carbonyl carbon, you want to keep that tucked in the back of your mind that might be something that could happen. You're going to, so that's going to be one thing, is that no, never mind. It's going to be very difficult to make that happen because although it's somewhat acidic, it's not wildly acidic. So you're going to watch for that as a factor, especially if there is a base present. That would be one, or that you have to have a base present for that to happen. In addition, you're going to have a nucleophile for that to react with, and you're going to see in 2 chapters when we use this again for something else that you're going to use this if your other options don't pan out. In other words, if your other options keep giving you the same molecule over and over again, then it's like this is the only thing that can make a different product, so then you start to think about this. So I'll try that one again. Anytime there's a base present, you're thinking that this is a possibility if there is an alpha hydrogen. In addition, if there are other options that create a different product for you, go with those because they're going to be easier reactions to do. However, if you don't create a different product as a result, then you might start thinking about this as well. Here's an example, and I hope I don't lose you, from 2 chapters from now. You can see that the carbon here has a good partial positive charge on it because it has the 2 oxygens withdrawing electrons. If you put the base in OH minus, then that would be attracted to this carbon, right? And the carbon would start to have 5 bonds, so you have to let go of something. You're not going to let go of a double bond, and you're not going to let go of a carbon. The oxygen would be better. But if you add an oxygen, an OH group, and then you take it off again, it's not getting you anywhere. That's a situation where you might say, I could use that OH to pull off the alpha hydrogen instead, because that might get me a different product. So that's kind of the illustration of what I'm telling you about. Okay, so if you have a base there, because you have to have a base to pull off the hydrogen, then you're always thinking about that. But then you're going to be prioritizing and saying, what are all my options for what reaction could happen? Pulling off of alpha hydrogen is going to be one of the last options that you use, though, because it's a little bit harder. Illustrate why an alpha hydrogen is somewhat acidic. I just showed you up here, but I'll do it again. So you have it in the right place in your notes. If a base pulls that hydrogen off, so that you create a carbanion, then that's going to have resonance. And if you're going to draw the resonance contributors for that, you have your group of 3. Within that group of 3, you're going to move the non-bonded electron pair away from the carbanion. The single becomes a double, the double becomes a single. So the actual molecule is going to be kind of a blend of those two.
How many electrons does the oxygen have in the first resonance?
Oh, sorry.
Oh.
Seriously,
You want?
what's exactly like the point?
Because I'm going to set you up for one thing. For one thing, like I said, we're going to be doing some reactions with it in a couple of chapters.
Oh, okay.
And the other thing, though, is that's important for ketoenol tautomerization, which is what I'm showing you next.
So I just kind of lost a little what exactly.
Yeah, what you're doing this for.
Yeah.
Yep.
Okay, cool.
Oh, I changed typefaces. Okay. So I think that I needed to have a little space for you to fill this part in, but I'll have to do that for the next go round. You don't know what a keto group is, and you don't know what an enol group is, so you don't know what ketoenol tautomerization is. So we'll go there first. You've heard of ketone bodies, right? If somebody has ketoacidosis or whatever. A ketone is where you have a carbon with a double bond oxygen, and it has carbon or hydrogen on either side of that carbonyl group. So this would be a ketone. And like I said, the next chapter we're going to be naming them. The chapter after that we're going to be reacting them. So you're going to see plenty of these.
Do you say what a ketone is one more time?
Sure, and actually I mislabeled this. It should have the hydrogen on there because otherwise. A ketone is where you have a carbonyl carbon with double bond oxygen, and then it has carbon, or, well, for it to be a true ketone, it has carbon on either side attached to it. For this description of ketoenol tautomerization, the ketone could be a not ketone also. It could have hydrogens or a carbon and hydrogen or whatever.
So as long as there's a carbon double bonded to oxygen.
Uh-huh. And then carbon at least on one side or maybe two. All right. Then if something has a double bond, it's an alkene. It has an -ene ending on it, right? And then if it has an alcohol, it's an -ol. And you know how you don't put the two vowels together, so you usually drop the E off? That's an -ene all once you put the hydrogen on there.
So it's a double bonded carbon with alcohol group.
Mm-hmm. An ene all. So you can see this resonance thing is how you get from a ketone to an enol. But the reason why it's not called resonance contributors, it's called tautomers, is because you're not just moving electrons around. Notice that you are going to remove this hydrogen here to get it going. And then in the end, this is going to pick up a hydrogen so that it can become an alcohol group. So you're moving electrons and moving atoms, and so it's not just resonance. That's called tautomers. When you're going back and forth because you're moving electrons and moving atoms.
Will it usually always be a catalyst, or will it usually always be like a catalyst in it, or is it going to be grabbing something else sometimes?
It'll always be hydrogen, specifically.
Okay.
Mm-hmm. So when you have ketones, they are always going to be converting into enols. And when you have enols, they'll be converting into ketones. And you're going to have an equilibrium mixture anytime you have a reaction in solution like this. If you're going from an enol to a keto group, it's exactly the opposite. You pull the hydrogen off of the OH group and move the electron pairs down, and then put the hydrogen on the carbon. Okay, but it always involves a carbanion at some point. And so carbanion stability is probably going to be the big issue. If you have multiple alpha hydrogens, which one you're going to remove? You'd want to form the more stable carbanion. All right, so why it's called that and how that moves, and yeah, I don't know if I feel like drawing this over again in this box, but the mechanism is just the same as I've got up here. So maybe I should get rid of that box. Since a molecule with a keto group could convert into two different enol compounds, in other words, you might have two different alpha carbons, so two different places you could remove the hydrogen. The way that you determine which enol form predominates is generally going to be the one that formed the better carbanion, I mean. Okay, so the big thing I wanted to get to today and allow you enough time so that it's not chopped off. Here's some practice for you for drawing the keto form of each enol and then drawing the enol form for the ketos that I have down below. As I said, within this area, notice that you already have a resonance box when you have an enol. So if you resonate the electron pair toward the carbon that has the pi bond you can let go of, and then you're going to create a carbanion there. Like that, right? Oxygen has a positive formal charge, and the sequence is going to differ a little bit depending on whether you're doing this under acidic conditions or basic conditions, but I don't want to get tangled up in all of that and have you memorize 10 different rules. The idea is now you got the oxygen with a positive formal charge, you got to take care of that. Carbon with a negative charge, you got to take care of that. And so the way to do that is remove the hydrogen from the oxygen so that you can get rid of the positive formal charge, and put the hydrogen on the carbon so that you can get rid of the negative formal charge. You're just swapping the hydrogen around. And that'd be the keto form. Okay, notice you're always working within 3 atoms there of the double bond and the oxygen with the non-bond electron pair. See what you can do with the next one. Told you were going to see lots of resonance from here on out. Do you have the correct answer for the next one? Except for remove the hydrogen from the oxygen, put it on where I have the negative charge.
My question, so the starting point for the first 2 would have been the enol, right? And the keto would have been the next one.
Yeah, so the molecule interconverts in solution, so it'll go back and forth between being a keto and enol.
Yeah.
You get a mixture of them, so I want you to be able to draw both ways, going both ways with it. All right, now we're going to go backwards the other way. So you have a keto group here, and you don't have resonance going on, so you want to set up the option for resonance by removing a hydrogen. So you notice before we resonated first and then did something with a hydrogen. Now we want to do something with a hydrogen and then resonate, if you're going back the other way. Notice that this carbon here doesn't have a hydrogen. It already has 4 bonds. There's no implied hydrogen there. Your only option is to remove the hydrogen from the CH3 group. Okay, so give that a try. Like a diamond, what have I done? Now, technically, the whole molecule is one big resonance system. So I've done something bad here by not doing that, but showing you. But we didn't cover aromatic compounds last semester, and you're generally not going to break up that ring of electrons. So that's why I didn't box it in, although technically it would be part of the resonance area. But you're only going to be working with this section right here, in case you were wondering. Okay, so that would be the enol product. You okay with that? If you are, go on to the next page. I've got 3 more. We're only going to be able to get to the first one. But what do you do if you have 2 different alpha carbons? For right now, what I want you to do is draw 2 different products, and we can go over which one would predominate next time.
The one that would just be H3.
That has a primary carbon ion, and so that one will be easier to form. The other one has a little bit better stability because it has more allylic carbons. So we'll go over that next time.
That's interesting.
This one represents this. I don't know.
If you have resonance already, resonate. If you don't, then you have to create it by removing the hydrogen. That's how you can kind of tell what you're doing the first step each time. The other 2 on the page, I guess you can do those for homework tonight. I'd like to clean this up so that we can start working on Diels-Alder reactions. Those are going to be tricky. They're going to take a while.